Hello all, welcome back. So last class we have discussed about a physical interpretation of a divergence. So what exactly the divergence is, then we defined about the divergence, then we went to the physical interpretation of that one. Then we got a result that a divergence of any vector is nothing but a flux per unit volume if that volume is very small. For example, we discussed about electric field, that is electric flux which is coming out of the surface of a particular unit volume. Similarly, today in this lecture we are going to discuss about divergence of a vector in a Cartesian coordinate system. So divergence of a vector in Cartesian coordinate system. So to find the value of divergence of any vector A using Cartesian coordinates, so we are going to consider in a particular system of a Cartesian coordinate system. Here I will take this axis as I'll take this axis as a x-axis, and I will take this axis as a z-axis, then this one as a y-axis, right? So here I'll consider a vector A at a particular point P, right? So I'll consider the particular point P. So let us take this parallel pipe, that is nothing but here I am taking a square, or it may be a rectangular, that is what we call the rectangular parallel pipe with a point P. So I will consider this point P here, this point as a P point, right? So I'll call this point P. Let I will define about the position of this one as, that is x, y, z. So x comma y comma z, it is at the center of with the edges of a length. Particularly, this is at the center. I will take, if I take this point as the center of the cube, then its edges of the length will be for a delta. In case of x-axis, I will consider this one as a delta x, and in case of y, I will consider this one as a delta y. So this is a delta y. From here to here it is a y-axis. Then here to here it is a x-axis. And similarly, if I consider along the z-axis, that edge length is, I'll take this one as a delta z. Right now, if I take this delta x, delta y, delta z as the edges of this parallel pipe, and they are parallel to the respective axis. Here, this is a z-axis, and this delta z is also parallel to the z-axis. And for delta x, it is parallel to x-axis. Delta y is parallel to y-axis. Right. Now, I'll consider the vector A at that particular point P with the position x, y, z. Then at point P, I can resolve this vector A. I can resolve this vector A into three rectangular components, that is AX, because it will be in I cap direction, and AY, it will be in J cap direction, and AZ in K cap direction. So I can resolve this vector A into three independent components which are parallel to the three rectangular coordinates, right? The value of the divergence of A now the value of a divergence of A vector is now equal to the, as we have defined in the last class, that is equal to the, it is a total flux or total outward flow, or total flux, or total um, outflow of a physical quantity, outflow of a vector quantity or physical quantity, vector quantity, right? Over a particular surface area. Here we have a 6 faces of a parallel pipe, because we have 6 faces. You can see in this particular system. Here I have, this one is a first face along x-axis, and this is second face. And I'll consider this top face as a fourth. This is a bottom as a 3, and the top as a 4. Then front one as a fifth one. Then backward, that last back face as a sixth face. There are 6 faces are there. Means the total divergence of this vector A is the total outward flow or outward flux coming out of 6 faces of a parallel pipe. 6 faces of a parallel pipe, right? Parallel pipe. Right. So means we need to consider that area. Flux is nothing but that quantity, physical quantity or vector quantity which is coming out of that fixed area. We call that one as a divergence. The outward flow over the front face, if I consider now in this diagram, if I consider the outward flow in the front face of along x-axis. So now if I take the only along particular axis, the outward flow over the front face of the block of this parallel pipe. Along the x-axis, I will consider this one is a front face. For x-axis, this is a front face. I will consider the component which is coming out of this face along x-axis. I will consider this one as ax component. Right? So now I'll consider this one as ax component. Now, if you look at this the coordinate of this P point along x-axis of a first phase, if I consider the same coordinate of this point x because it is at a position x. Now here I have taken this edge length as delta x. Now from this particular P point, this distance is actually the x plus delta x by 2. It is x plus delta x by 2 because this half length is nothing but this is delta x by 2 and this is also delta x by 2. Now if you take the position of this particular P point for this front face, I will call this one as a P1 point for along the x-axis. The coordinate of P1 at the center of the first face are now x plus x by 2 for x-axis. Similarly for y, we can define this one as y and z, right? Then if I take the same P point coordinate in a second phase at this second phase, I will call this one as a P2. Then now if you define the position of this one, now it is x minus delta x by 2 because here it is backward with the minus x by 2. So minus delta x by 2. This is delta x by 2 and here is delta x by 2. So it is here it is a plus sign, this side this is negative sign. So that's why if I define the coordinates of this same 2 points in both the faces, here I will define for first phase, the coordinate of that P point are x plus delta x by 2 into yz because y and z are same for the that particular point. Then because P lies at the center of the block of that particular phase 1, then if you see the and similarly if you see that particular P point coordinate at the center of the second phase, at the center of a second phase, that P point coordinates will become x minus delta x by 2 and y comma z because here if you see this phases 1 and phase 2, the positions of first point P and phase 1. Similarly for second phase, that is P2, this coordinates are x plus delta x by 2 comma y comma z. Then for P2 this becomes x minus x by delta x by 2 and y comma z. So these are the coordinates of that particular point. Now the rate of flow of a vector A along x-axis is ax. So this is the rate of flow of a vector along x-axis, right, at a point P, at point P here, and that rate of flow of a particular function or a vector is defined as dou ax divided by dou x because it is the rate of the change of that particular ax component along x-axis. So this is totally given by, in terms of delta x, we can write this dou x by x as that means rate of flow along x-axis is now given by, that is ax plus dou ax by dou x dot delta x by 2 because this flow is in the direction of x. With the first phase we define this one as delta x by x into delta x by 2 because it is now in the direction of a phase 1. It is in the direction of phase 1 here, right? So phase 1, I'll call this equation as a 1 equation. Then similarly if you calculate the same outward flow along total coordinate system, so now therefore the total flow of a vector on the front face including x y z coordinates means both y and z coordinates. Now this becomes ax plus dou ax divided by dou x into delta x divided by 2. This is only allowed for x-axis. Similarly for y, that is given by delta y and delta z, because there is only, it is this component only dependency of a y and z. Therefore we are going to consider, so not, it is not dependent on y and z. Therefore we are going to consider only x along with y and z components. Right. So it is totally depends on only x-axis. Similarly, if you calculate the inward, means that is outward direction, the net flow of the vector in second phase, if we calculate, because this if this axis, this A is coming out when from first axis, then it is coming into the first, sorry, this is AX is coming out of first phase and it is entering into the second phase, that I will call this one as the same AX. Now, if you calculate the rate of net flow of that vector along second phase, through the second phase along or along x direction is given by, similarly, if you calculate the net flow of a vector from second phase is given by ax minus dou ax divided by dou x into delta x by 2, because it is, now it is about the inward flow, because here from first phase it is coming out, that's why we consider this one as an outward flow. Then here I will consider this one as an inward flow. This is delta y into delta z, only dependence on x, it is only ax component, that's why it is x derivative, so it is inward flow. Similarly, if you calculate for other components also you can get, but we'll see first what exactly that total net flow of a vector from first phase to second phase, right? So total net or total or net flow of the vector from the first and second phase, because one is inward, another one is outward. Therefore the total flux is given by the sum of these two fluxes, or sum of two of flow rates, that is given by, first one is ax plus dou ax divided by dou x into delta x by 2, right? Same into delta y and delta z are there, minus the same out, this is inward flow, that is minus of ax minus dou ax divided by dou x into delta x by 2 into delta y and delta z, right? So this is what the total flow. Now if you add these two, then it becomes that is only I will get the component ax delta y delta z plus dou x into delta x by 2 into delta y into delta z minus ax into delta y into delta z plus dou ax divided by dou x into delta x by 2 into delta y into delta z, right? Now if you see this, there are two components, so these two terms will get cancelled, this term and this term, then I'll be remained only with 2 times of dou ax divided by dou x into delta y into delta z, right? So this is what similarly there is another one term is also there, right? So delta x by 2 now 2 get cancels, I'll be remained only with dou ax divided by dou x into delta x delta y and delta z. So this is the total net flow of vector A along x-axis. This is net flow along x-axis. Similarly, if you go for the net flow of that vector along y-axis, similarly we get Similarly, only a net flow of vector A along y-axis is given by, that is along y, that is given by dou ax divided by uh, this is dou ay because it's a y component, dou ay divided by dou y into delta x, delta y, and delta z. Similarly, along along z axis, so this is, I will call this is both z and y axis. So along z axis, so I get dou az divided by dou z into delta x into delta y into delta z. Right now, if you take the total net flow of means a total flow of a vector per unit value, therefore by taking the, because we have considered only along these, this is about y faces and this is about z faces, right? Because the whatever the flux coming through the y axis here, so whatever the flux coming out of this y axis is along this direction, this is along y direction, and this is along x direction here, and this is along z direction. So if you take the inward of this in this z direction, that is from that face. So all these three are the fluxes. If you calculate the total flow rate of that vector through that unit volume is given by, that is a net flow of a vector per unit volume is given by, that is we need to add all the three components per unit value, that is dou ax divided by dou x plus dou ay divided by dou y plus dou az divided by dou z into bracket, that is delta x, delta y, and delta z. Here, because I have taken the per unit volume, that unit volume element of a particular system is given by delta x, delta y, delta z. So means that unit per unit volume is given by, that is delta x, delta y, delta z. So as I have defined that net flow of a vector per unit value, because this is totally whatever I have written here, this is about total flow only. Per unit volume is given by delta x, delta y, delta z. Alright, so it should be z, right? Okay. Now, if you cancel these two terms, if you cancel these two terms, then I will be only remained with the term that is given by a net of flow per unit volume through the closed surfaces, that is given by dou ax divided by dou x plus dou ay divided by dou y plus dou az divided by dou z, right? So as we already know that, what about the net flow per unit volume is given by, net flow per unit volume is nothing but a divergence of a vector A. We already know this. Divergence of a vector A is nothing but a dou ax divided by dou x plus dou ay divided by dou y. Similarly, dou az divided by dou z. Now I can write this total equation in terms of a del operator, that is nothing but it is del dot A. That is nothing but a divergence of a vector A, right? So here both vector A and this differential operator both are vector quantities. So this is what the divergence of a vector in case of a Cartesian coordinate, that is totally given by, that is del dot A vector. Both are vectors. If you take the dot product of those, means that is nothing but a divergence, that is given by dou x divided by dou x plus dou ay divided by dou y plus dou az divided by dou z. Here x, y, z are the Cartesian coordinates, and the particular ax, ay, az, these three are individual components of a vector A along x-axis, y-axis, and z-axis. So this is what it actually mathematically divergence is defined. And take some problems to submit on a Google Classroom as an assignment. The first question is, Evaluate the divergence of function u, that is x power 4 I cap plus y power 4 j cap plus z power 4 k cap, right? So here it is of z y power 4, this is y power 4 j cap. So that is nothing but x power 4 I cap plus y power 4 j cap plus z power 4 k cap at point 1 comma 2 comma 2, right? Evaluate the divergence of a vector u. This is the vector at point 1 comma 2 comma 2. Then similarly, second question is uh, calculate the divergence of, or evaluate the divergence of function f is equal to 4x square I cap plus that is 4 xy j cap plus z square k cap, right? Then third question is calculate the gradient that I have discussed in the previous two classes, that is a gradient. Evaluate the grad of phi if phi is equal to log of x square plus y square plus z square. So these three are the questions you need to submit in a Google Classroom by referring a gradient and divergence of a particular functions, right? So okay, thank you.